Welcome to another lesson on Technical Sciences Grade 12. It is the 28th of September 2020. It is a Monday, and I really hope that you had a good start to the week at school. And you are also going to have a good start with me today for physical properties of organic compounds. And why are we dealing with physical properties? Because it is also another section in organic chemistry that we have to learn. You will remember that we have learned a nomenclature of organic compounds, which is the first section of the work. Then another section that we have learned in organic chemistry was on organic reactions. And the last section that we are looking at today is the physical properties of organic compounds. So as I have mentioned to you, my dear learners, before, that for you to really do well in physical properties as well as organic reactions, the basics are in nomenclature, understanding molecules, right? Understanding your organic molecules, all the basics in terms of organic molecules, they are really critical for you to do well in terms of this section, which is physical properties. So I really hope that you are ready to enjoy this lesson with me. Make sure that you have a pen with you and you also have your notebook so that you are able to take down the notes of important things that I'm going to highlight for you. So we go straight into the structure of the lesson for today. It will be an overview, and that is where we are going to look at physical properties as per the examination guidelines. Remember, everything that we learn, we make sure that we tick the boxes in the examination guidelines to say, yes, we have done this one, yes, we have done this one, and then those that you haven't done, then you don't tick them. But you know that in preparation for the examination, you have to know everything that is in the examination guidelines. And furthermore, in this section on the overview, there are quite a number of things that I want to highlight based on your examination guidelines and what you are really expected to know, particularly in definitions, but we will talk about that. Then, secondly, in features of the topic, that is where we are basically going to learn physical properties. We will just go deep into it and learn the theory behind it. And then for our assignment, we will look at a question at least, just one for now, on physical properties to really concretize what we have learned over the course of this particular lesson, to see if we really understood what we have learned. And lastly, I will be giving you tips about how to prepare for this section of the work when you prepare for your exam, as well as the mark allocation that we give to this particular topic. So hopefully you are ready for me, and we go straight into the first section, which is the overview, where we learn what the examination guidelines really expect of us. Firstly, we will understand the relationships of physical properties altogether. And in particular, we will focus on the boiling point, we will focus on the melting point, and we will focus on the vapor pressure and not necessarily the viscosity. So we are going to learn about the boiling point, the melting point, as well as the vapor pressure. Then under this section, we must be able to discuss relationships in physical properties of alkanes, alkenes, alkynes, alkyl halides, which is also what we call haloalkanes, aldehydes, ketones, alcohols, carboxylic acids, and esters. So we are going to learn the physical properties of all these homologous series. Then we must be able to compare the physical properties of different homologous series. We must be able to compare them. In other words, I must be able to talk about a physical property of an alkane versus the physical property of an alcohol, or an alkene versus an alcohol, or any of the homologous series here. I must be able to compare their physical properties, meaning why are they different and so on. Then, for a given example, from the above functional groups, basically from these homologous series, because they have different functional groups, we must be able to explain the relationship between physical properties and the strength of intermolecular forces. That is, we must be able to talk about hydrogen bonds. We must be able to talk about dipole-dipole forces, and we must be able to talk about induced dipole forces. And this induced dipole forces, you must know their other name, the one that we commonly use. And we refer to induced dipole forces as London forces. So you will see most of the time we talk about London forces, but we know they are called induced dipole forces. So we'll talk about the strength of intermolecular forces. In other words, when you talk about hydrogen bonds, when you talk about dipole-dipole forces, and when you talk about induced dipole forces, or what we call London forces, you must know that we are talking about the types of intermolecular forces that we get in different organic molecules, depending on which homologous series they belong to. So we must be able to compare the strength of these intermolecular forces. As well, we must be able to talk about the type of functional groups. And the type of functional groups actually determines the types of intermolecular forces. So the type of functional group that we get in an organic molecule, it definitely determines the type of intermolecular forces. In other words, the type of intermolecular forces that you get in an organic molecule, it actually depends on the type of functional group that molecule has altogether. In other words, my dear learners, as we go deeper, you will understand what do we mean when we say the type of functional group actually will determine the type of intermolecular forces. Right, so just note that. Then we must be able to talk about the chain length as well altogether. Right, so we must be able to talk about the relationship between chain length and a particular. Again, I want you to note this, right? Because I just wanted to show you what your examination guideline is saying and what is also critical for you to know, which makes your work quite easier. And also when you study, you will see that some textbooks will be referring to chain length. Other textbooks could be referring to surface area. You must know when you talk about the length of the chain, we actually are referring to the surface area of the molecule altogether. And also the branched chains, because the branched chains actually talk to the chain length altogether, and they basically talk to the surface area. In other words, we are expected to know how the strength of intermolecular forces, how the type of functional groups or the types of intermolecular forces, and how the chain length, or what we call the surface area, actually affects any of these physical properties that we are talking about here, which is the boiling point, the melting point, as well as the vapor pressure. So we must be able to talk about that, which is essentially the lesson for today. Then, my dear learners, this is not in your examination guidelines. It does not appear on your examination guidelines, and you are required to know this. And regardless of whether it's not appearing, my dear learners, remember now, we can't talk about these physical properties without actually defining them. And hence, it is important that you know their definition, because that is also going to help you seal thoroughly the knowledge that you are going to learn when you do physical properties of organic compounds. And as mentioned, the physical properties are your boiling point and your melting point, as well as the vapor pressure. So these three definitions, my dear learners, you have to know them. And even if you go to previous examination papers, you will see that we do ask you to determine, rather to define the term boiling point. We do ask you to define the term melting point, and we do ask you to define the term vapor pressure. And those are the definitions altogether, right? And we will revert back to them as we continue to learn what physical properties are about. But I want you to take note of these particular definitions. So if you don't have enough time to write them, please ensure that you can always log in and really just take note of these particular definitions. So now we actually begin our lesson. And I want to begin our lesson by actually defining what boiling point is, what melting point is, and what vapor pressure is. And remember, all these three, we refer to them as physical properties. We refer to these as physical properties. So these are the physical properties of organic compounds that we are going to learn. Now, if you remember, when we were doing nomenclature, we had one definition that we learned, and that was the definition of a functional group. And we know each homologous series has its own functional group altogether. For example, when you look at alkenes, the functional group is the double bond between carbon and carbon atoms. When you look at an alkyne, the functional group is the triple bond between carbon and carbon atoms. When you look at alcohols, the functional group is the OH that is bonded to the carbon, what we refer to as the hydroxyl group. When you talk about aldehydes, for example, we know the functional group is the formyl group. When we talk about carboxylic acids, we know the functional group is the carboxyl group. Now, these molecules, they have different functional groups altogether. And if they have different functional groups, it means they are also going to have different physical properties, and they are also going to have different chemical properties. Now, what do I mean when I say they are going to have different physical properties? For example, if you look at an alkane, for example, a pentane, and you look at an alcohol, for example, pentanol, they have different functional groups altogether. The functional groups are not the same. And therefore, I cannot expect a pentane to have the same physical properties as a pentanol. In other words, I cannot expect pentane to have the same boiling point, or to have the same melting point, or to have the same vapor pressure as pentanol. Why? Because they don't have the same physical properties altogether. The boiling point and the melting point and the vapor pressure are going to be different. Why? Because the functional groups are also different. Also, in terms of chemical properties, they cannot have the same chemical properties. In other words, they cannot react in the same way. Why? Because the functional groups are different. And that is why when we were defining the term functional group, we said it's an atom, a group of atoms, or a bond that determines the chemistry of a molecule. I will repeat that for you. It's an atom, a group of determines the chemistry of a molecule. So the functional group determines the chemistry of a molecule. It determines how a molecule will react. Another definition that we give you in your examination guidelines for the term functional group is to say it's an atom, a group of atoms, or a bond that determines the physical properties and chemical properties of organic compounds. In other words, the functional group of an organic molecule will determine its boiling point, its melting point, and its vapor pressure, which are the physical properties. But also that functional group will determine the chemical properties, which are how that molecule is going to react. And we have done that in the previous week when we were doing organic reactions. So different molecules, or rather different organic molecules, have different boiling points, they have different melting points, and they have different vapor pressure. Now, my dear learners, when we define boiling point, we say it is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. Now, this is where the definition actually ends. This section here, from the stronger the intermolecular forces, the higher the boiling point, is simply giving you the relationship between intermolecular forces and boiling point. What you need to give us when we ask you for the definition is the part that is in bold. In other words, you need to be able to give these definitions. Furthermore, my dear learners, you need to be able to remember these definitions, and you need to understand them. So firstly, boiling point is a particular value. It's a particular value of temperature. That is why when the definition begins, it says the temperature. we don't need to confuse this with boiling, because boiling is a process altogether. A substance is changing its state, but boiling point, a particular point, a particular value of temperature. We say it is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. In other words, the pressure that is formed by the vapor, when it is equal to the atmospheric pressure, in other words, the pressure that is on the outside, the external pressure, then we know at that particular temperature, it is the boiling point, because now the vapor pressure of that substance is going to be equal to the atmospheric pressure. So that temperature, when these two pressures are equal, we refer to that as the boiling point. And you need to know that a molecule that has a higher boiling point means that it has stronger intermolecular forces. Now, what do we mean when we talk about intermolecular forces? We are talking about forces that you get between molecules, not forces within the molecule. Altogether, the forces within the molecule, we refer to them as interatomic forces. Here, we are talking about intermolecular forces. So the forces that you get between molecules. Remember, when you have a container or a reaction vessel, there are trillions and billions of molecules, and those molecules have forces between them altogether, and those forces between them are referred to as intermolecular forces, and you have to be very careful of that altogether. Do not confuse it with molecular forces or interatomic forces. So these are intermolecular forces. And if the intermolecular forces are strong, then the boiling point is going to be high altogether. Then we have the definition of the melting point. Now, firstly, we can see that it is a point. In other words, it is a particular temperature. It is the temperature at which the solid and liquid phases of a substance are at equilibrium. It is the temperature at which the solid and liquid phases of a substance are at equilibrium. Now, how do you know that you need to talk about solid and liquid? Because you know that when a substance is actually melting, it is changing its state from the solid state into the liquid state, or the solid phase into the liquid phase. So when the two phases of that substance are at equilibrium, then that particular temperature, when they are at equilibrium, we refer to that as the melting point. Another definition that you need to know is the definition of the term vapor pressure. Now, when we define vapor pressure, the first part of the definition is to say it is the pressure. And we know it is the pressure. Why? Because we are defining the term vapor pressure. So you can't start in any other way except to say it is the pressure. Now, which pressure is that? It is the pressure that is exerted by a vapor, right? Why are we saying it is the pressure exerted by a vapor? Because it is the vapor pressure. It is the pressure exerted by a vapor. So you know the first part of the definition. At equilibrium with its liquid. Now, why is it with the liquid? We know when vapor forms, it is because a substance is actually changing its phase, or we say it is actually changing its state from a liquid to a gas, or liquid to a vapor. And hence, the definition says it is the pressure exerted by a vapor at equilibrium with its liquid. In what? In a closed system. Altogether. And we are told again, the stronger the intermolecular forces, the lower the vapor pressure. Now, what does that tell us? It tells us that if the intermolecular forces are strong, then the vapor pressure is going to be low. Just to revert back to the boiling point again, my dear learners, we can see that when the intermolecular forces are stronger, the boiling point is high. Now, I want us to actually compare the relationship between boiling point and vapor pressure and the strength of intermolecular forces. Now, we can see that if the boiling point is high, then the intermolecular forces are strong. If the vapor pressure is low, then the intermolecular forces are strong. So what does this tell me about the intermolecular forces and boiling point and vapor pressure? It tells me that if the boiling point is high, then the vapor pressure is low. Why can we say that? Because the boiling point, when it's high, that is when the intermolecular forces are strong. The vapor pressure, when it's low, that is when the intermolecular forces are strong. In other words, the higher the boiling point, the lower the vapor pressure. What is common about this relationship is that it happens when the intermolecular forces are stronger. So it means the stronger the intermolecular forces, the higher the boiling point is going to be, but the lower the vapor pressure is going to be. And the relationship is also going to be vice versa. If the intermolecular forces are weaker, then it means the boiling point is going to be low, but the vapor pressure is going to be higher. In other words, this relationship goes vice versa as well. In other words, I could say the weaker the intermolecular forces, the lower the boiling point. Furthermore, I could come here and say the weaker the intermolecular forces, the higher the vapor pressure. So the vice versa is also true. The opposite is true. Now, let us look at melting point and boiling point. We can see the stronger the intermolecular forces, the higher the boiling point. Again, the stronger the intermolecular forces, the higher the melting point. So what does that tell me? It tells me that if the boiling point is high, it also means the melting point is high, meaning the intermolecular forces are stronger at that time. The opposite is true. If the intermolecular forces are weak, the boiling point will also be lower. If the intermolecular forces are weak, the melting point is also going to be low. What does that teach me, my dear learners? It shows me that the higher the melting point at a given time, the higher the boiling point is also going to be, because both of them at that time, the intermolecular forces are going to be strong altogether. And the opposite, we said, it's true. Now, let us look at melting point again and vapor pressure. Now, the stronger the intermolecular forces, the higher the melting point is. Again, the stronger the intermolecular forces, the lower the vapor pressure. So what does that tell me? It means at the same time the intermolecular forces are strong, the melting point will be high, but then the vapor pressure is going to be low altogether. What does that teach me, my dear learners? It teaches me that the higher the melting point at a given time, the lower the vapor pressure is going to be, because at that time the intermolecular forces are equally strong altogether. And the opposite will be true, meaning when the intermolecular forces are weak, the melting point will be lower. But when the intermolecular forces are weaker, then the vapor pressure is going to be higher. So this is a section which does not appear on your examination guidelines, but you need to know that because we will ask you to define the term boiling point, we will ask you to define the term melting point, and we will ask you to define the term vapor pressure. Right, we continue. Now, let us go again and revisit this relationship that I was talking about here. Physical properties of organic compounds that we are going to look at again, my dear learners. As a reminder, we said it's boiling point, it's melting point, and it is vapor pressure. So let us first talk about the relationship between vapor pressure and boiling point. And I have told you that compounds with high boiling points, they are going to have a low vapor pressure. And that's where we said the higher the boiling point, the lower the vapor pressure, and the opposite is true. The lower the boiling point, the higher the vapor pressure. Then let us talk about physical properties and intermolecular forces. Now, the physical properties of compounds definitely depends on the strength of intermolecular forces, those forces that you get between molecules. What does this tell us? It tells us that the boiling point, the melting point, and the vapor pressure of different organic compounds depend on the strength of the intermolecular forces, which is what I was telling you to say. The stronger the intermolecular forces are, right, the higher the boiling point, the higher the melting point, but the lower the vapor pressure is going to be. And you need to understand that thoroughly. If the intermolecular forces are strong, the boiling point will be high, melting point will be high, but the vapor pressure is going to be low. The opposite is true, my dear learners. The weaker the intermolecular forces, the lower the boiling point, the lower the melting point, but the higher the vapor pressure. So remember that the opposite is true. Now, we are going to look at different types of intermolecular forces. But for now, I want to introduce you to hydrogen bonds. So we will look at hydrogen bonds. We will look at London forces. We will look at dipole-dipole forces. Now, I know you already have pre-existing knowledge on this section, and some of you are aware of what we refer to as van der Waals forces. Now, all these types of intermolecular forces that we look at, right, in our syllabus, we classify them as van der Waals forces. So even when we're talking about hydrogen bonds and London forces and dipole-dipole forces, just know that we are referring to those van der Waals forces. And therefore, to make this work easy for yourself and to ensure that when we mark you, we talk about you are referring to correct types of intermolecular forces at that time. Let us agree to stick to hydrogen bonds, to stick to London forces, and to stick to dipole-dipole forces. Now, strong hydrogen bonds, you only get them between molecules in which a hydrogen atom is covalently bonded to a nitrogen atom, an oxygen atom, or a fluorine atom. But for our syllabus, we are going to look at those hydrogen bonds that we will be getting in alcohols and carboxylic acids, because we don't deal with those molecules where we have nitrogen atoms and fluorine atoms. And therefore, for our syllabus, it means these hydrogen bonds, we are going to get them in organic molecules that are alcohols and carboxylic acids. So when you see an alcohol, you know that it has those special intermolecular forces that we call hydrogen bonds, as well as those that we refer to, rather, your alcohols and your carboxylic acid, they have those hydrogen bonds, which are types of intermolecular forces. And naturally, these hydrogen bonds are strong. They are very strong intermolecular forces that you get in alcohols and carboxylic acids. In other words, my dear learners, given a question and you are required to identify the types of intermolecular forces, when you see alcohols, you know that you have to talk about hydrogen bonds altogether. And for now, I don't want to confuse you and talk about the London forces that you also get here in these alcohols and carboxylic acid. Let us not worry about that for now. Know that for your syllabus and how we will ask you questions, the most important intermolecular forces that you will need to identify for us when you see organic molecules of alcohols and carboxylic acid is you talking about hydrogen bonds, and also remembering that these hydrogen bonds are strong. Furthermore, in terms of hydrogen bonds, my learners, you must know that the hydrogen bonds in carboxylic acids, they are stronger than the hydrogen bonds of alcohols altogether. So remember that, and I am actually just going now to show you why we say that. Right. Now, let us look at alcohol molecules. Alcohol molecules, we say they have one side for hydrogen bonding. And you look at carboxylic acids, we say they have two sides for hydrogen bonding. Now, let us look at why alcohols actually have one side for hydrogen bonding. When you look at these molecules, this is one molecule of an alcohol. This is actually methanol. This one is also methanol. Remember, the hydrogen bond will exist between the oxygen of one molecule and the hydrogen of another molecule. And that is a hydrogen bond, this bond here. So we can see that it has just one side for hydrogen bonding because of that atom there of oxygen. Then Our carboxylic acids, we can see that they have two sides for hydrogen bonding, and you can see it's a side with a T. It's not a side, it's a side. So let us look at these two organic molecules. Can you see, my dear learners, on this oxygen atom, there I have a hydrogen bond between that oxygen and the hydrogen. So there is a hydrogen bond. Another hydrogen bond that we have is between this oxygen as well as that hydrogen. So we have two sides for hydrogen bonding. So in essence, what we are seeing here is that alcohols only have one side for hydrogen bonding. So it will make less hydrogen bonds as compared to carboxylic acid, which has two sides for hydrogen bonding. And as a result, carboxylic acids will have stronger hydrogen bonds compared to alcohols. And the main reason is because carboxylic acids have two sides for hydrogen bonding and alcohols have one side for hydrogen bonding. So you need to know that when you are required to explain why the boiling point or the vapor pressure or the melting point of alcohols differs with those of carboxylic acids. But my dear learners, remember again, even though carboxylic acids have stronger hydrogen bonds than alcohols, it doesn't mean the hydrogen bonds of alcohols are weak. They are still very strong actually. Altogether, it's just that those of carboxylic acids are stronger than those of alcohols. So those are the first types of intermolecular forces that I want to introduce to you. And later on, we will talk about other types of intermolecular forces. Now, I want to now teach you what our examination guideline tells us. Remember, according to the examination guidelines, we are saying for a given physical property altogether, or any of these functional groups, we must be able to explain the relationship between physical properties and the strength of intermolecular forces, the type of functional groups, the chain length, and the branch chains. So now we are dealing with this section of the work that the examination guidelines requires of us to know. Then we say, okay, let us first learn the relationship between boiling point, melting point, melting point, and vapor pressure. And all these three physical properties, we are going to relate them to the chain length. And remember what I said about chain length? We said we can also refer to that as the surface area. As the surface area. Now, let us look at this molecule. This molecule is propane. If you really show the carbons and the hydrogens and you draw it thoroughly, this will be propane, this one will be butane, and this one will be pentane. Why propane? Because it has 3 carbons and 8 hydrogens. Why butane? It has 3 carbons, 10 hydrogens. Rather, it has 4 carbons and 10 hydrogens. Why pentane? Because it has 5 carbons and 12 hydrogens. Now, when you go from left to right, in other words, when you go from propane to butane to pentane, what you can see is that the chain length is increasing. Why is the chain length why are we saying the chain length is increasing? because the longest chain of carbons without breaking, which is the parent chain, here it had 3 carbons. Then here it had 4 carbons, so the length of the carbon chain is increasing. Here we had 5 carbons, so the length of the carbon chain is increasing. Altogether, my dear learners. And what does that tell me? It tells me that the chain is increasing, rather the chain length is increasing from left to right. Altogether. So when the chain length is increasing, we can also say that the surface area is then increasing altogether. So know that. Now, when the surface area increases, it means the strength of the intermolecular forces is also increasing. In other words, when you increase the length of the chain, meaning 3 carbons long to 4 carbons long to 5 carbons long, it means you are making the intermolecular forces to be strong. It means that the intermolecular forces of propane are weaker than those of butane, and those of butane are weaker than those of pentane. So the intermolecular forces are increasing as you go from left to right. And they are increasing because the chain length is increasing altogether. Now, when that is happening, it means then the boiling point is also increasing. How do we know the boiling point is increasing? Because we said the stronger the intermolecular forces, the higher the boiling point. So when the intermolecular forces are getting stronger, it means the boiling point is also increasing altogether. And again, it means there is also an increase in the melting point, because we said when the intermolecular forces become stronger, it means the melting point is also increasing. But then what does that tell us about the vapor pressure? The vapor pressure is decreasing. So you need to know that altogether. And when you look at these molecules, we can compare their boiling point based on the chain length. Why? Because all of them, they have what we call London forces. They have London forces. London forces are those intermolecular forces that you get on the hydrocarbon chain. So this hydrocarbon chain only has London forces. This hydrocarbon chain only has London forces. This hydrocarbon chain only has London forces. And as a result, the boiling point becomes different because of the intermolecular forces becoming stronger, because of the London forces becoming stronger because of the chain length. And hence, we have to talk about the chain length. Why? Because we are comparing molecules of the same homologous series. In other words, when we look at the same, when we compare molecules of the same homologous series, they contain the same types of intermolecular forces. So the intermolecular forces, the type of intermolecular forces are not significant here in terms of why the boiling point is changing. What is significant in terms of why the boiling point is getting higher is those intermolecular forces becoming stronger because of the chain length increasing altogether. So every time you see, we ask you why the boiling point of propane is different to that of butane and pentane and so on, or why the boiling point increases from propane to pentane. you must then check that, oh, these molecules belong to the same homologous series, and therefore it means the chain length is increasing. In other words, you cannot talk about the different types of intermolecular forces. Why? Because the intermolecular forces are the same. They all contain London forces. Altogether, my dear learners. So remember that, right? And that is why I said, let's not talk about van der Waals forces because you are going to confuse yourself. Talk about London forces, right? We continue. Then we talk about the relationship between boiling point and vapor pressure, as well as the branching, because this branching will actually affect the surface area altogether. It will affect the surface area. In other words, it will affect the chain length. Now, let us check at what is happening from right to left. When you look at this chain, it is 5 carbons long. It's one, two, three, 4, 5 carbons long. The longest chain without breaking is 5 carbons long, which is the parent chain. It's a pent. Then you look at this molecule. Can you see that this molecule, the longest carbon chain without breaking, it's 1, 2, 3, 4. So the parent chain is a bute. It has 4 carbons. And then there is a branch there altogether. There is a substituent. Then you come to this molecule. The longest chain without breaking is 1, 2, 3 carbons. Even if you look at it like this, 1, 2, 3 carbons, or 1, 2, 3 carbons. So the longest chain, which is the parent chain without breaking, it's prop. And then if I numbered carbon 1, carbon 2, carbon 3, it means this carbon and that carbon is the substituent. And if you look at this one, there is only one substituent. So this one, we can see it's a straight chain. And then if you look at this molecule, it is a branched chain because there is a branch there, but this one is less branched. Then if you look at the other molecule, it has 2 branches. So this one is more branched. Now, let us look at what is the impact of branching. Because when you start from left to right, we can see we have a straight chain, we branch it a little bit, and we branch it some more. Firstly, what you should see there is that the impact of branching reduces the size of the parent chain. The size of the parent chain here is 5 carbons long, it's pent. The size of the parent chain is 4 carbons long, it's a bute. The size of the parent chain here is 3 carbons, it's a prop. So the molecule is actually becoming smaller in terms of surface area because this is 5 carbons long, this is 4 carbons long, so it becomes less. This is 3 carbons long. In other words, from right to left, the branching increases because here there is no to dimethyl propane, there are 2 branches. So it's less branch because of 1 branch, it's more branch because of 2 branches. In other words, from right to left, the branching is increasing. In other words, the surface area is decreasing because the parent chain goes from 5 carbons long to 4 carbons long to 3 carbons long. And that is why when you talk about increasing branching, we are talking about decreasing the surface area. Or another learner could have said say we are actually decreasing the chain length. Now, when the length of the chain or the surface area decreases, then we definitely know that the strength of the intermolecular forces is also decreasing. And we know when the strength of intermolecular forces decreases when you go from right to left, it means the boiling point is decreasing altogether. And it also means the melting point is decreasing altogether. Why? Because the weaker the intermolecular forces, the lower the boiling point and the lower the melting point. But then when the intermolecular forces decrease in strength from right to left, then we know the vapor pressure is going to increase. And the vice versa is true. When we go from left to right, we can see that it was more branched, then it became less branched, then it became a straight chain. So the branching decreases from more branched to less branched, and from less branched to no branch altogether, which is a straight chain. So what do we see? The size of the parent chain increases from prop to but to pent, meaning from 3 carbons long to 4 carbons long, which is the parent chain, to 5 carbons long. So it means the branching is decreasing and therefore the surface area is increasing. And we know when the surface area increases, the strength of the intermolecular forces is also going to increase. And we know the stronger the intermolecular forces, the higher the boiling point. So we will have an increase in boiling point from left to right, which also means we will have an increase in the melting point. But the vapor pressure is going to decrease. Why? Because we know that the stronger the intermolecular forces, the lower the vapor pressure. Again, when we are asked to actually look at why the boiling points are different, it is actually because of this surface area or the chain length and not because of the types of intermolecular forces. Why? Because they all have the same type of intermolecular forces. They belong to the same homologous series. Right. Lastly for today, my dear learners, I want us to look at the relationship between the boiling point and the type of functional group. And I want you again to remember that the functional group, the type of functional group actually determines what? The type of intermolecular forces. It affects the type of intermolecular forces that you will get in that particular molecule altogether. Right. Now, let us look at these molecules from left to right. Firstly, here I have pentane. So pentane only contains a hydrocarbon chain, and that is why we say it only has London forces, which are your van der Waals forces. Can you see everything here? It's van der Waals forces. When we look at butanal, this is an aldehyde. So it still has that part, which is the hydrocarbon chain. And that is why it actually has London forces. But it also has that part, which is polar in nature. And therefore, it has those dipole forces. And you look at an alcohol, it still has that hydrocarbon chain, so it has the London forces. It is polar, so it has dipole forces, but we also know that it has hydrogen bonds. Now, my dear learners, to make this work easy, when we talk about hydrocarbons, London forces, you will get them in hydrocarbons. In other words, the most important forces that we must identify, it's London forces. Then when we talk simply hydrogen bonds, we've already talked about this. We said you will get them in your alcohols and carboxylic acids. Now, we are not saying there are no London forces. We are not saying there are no dipole-dipole forces. They are there, my dear learners, but please, to make sure that you pass, and also how we mark you. When you talk about just refer to hydrogen bonds only when you talk about alcohols and carboxylic acids. And then the remaining homologous series, you will just refer to dipole-dipole forces altogether, which are the remaining. Meaning, when we talk about hydrocarbons, London forces, most important in alkanes, alkenes, alkynes, because they are your hydrocarbons. When you talk about hydrogen bonds, alcohols, and carboxylic acids, then when you talk about the rest, it will be your haloalkanes, it will be your aldehydes, it will be your ketones, etc. Those that are remaining, and we will then refer to dipole-dipole forces. Now, when we talk about London forces, you need to take note that they are the weakest of all intermolecular forces. When we talk about hydrogen bonds, you must know that they are the strongest of all intermolecular forces. And dipole-dipole forces, they have a strength that is greater than those of London forces, but they are weaker than hydrogen bonds. So we basically say they have medium strength altogether as compared to these two, as compared to the London forces and the hydrogen bonds. Now, what does this teach me? It is basically teaching me that when I go from left to right, there's an increase in the polarity of the functional group. Now, to make it easy for yourself, just say, if there's an increase in the polarity of the functional group, we are simply saying there is an increase in the strength of intermolecular forces. Why? Because we are going from weakest strength to medium strength to the strongest strength altogether, or rather to more stronger intermolecular forces. As a result, these intermolecular forces, my dear learners, as you go from left to right, we said in this one, the most important are London forces. In these ones, aldehydes, which is your butanol, the most important are dipole forces. In alcohols, the most important are your hydrogen bonds. So the intermolecular force strength is increasing from pentane to butanol and to butan 1-ol. So if the strength of intermolecular forces increases, then it means the boiling point is increasing. And we also know that when the intermolecular forces increase in strength, the melting point is also increasing. But we know that when the intermolecular forces become stronger, then the vapor pressure is decreasing altogether, my dear learners. So know this particular relationship. So tomorrow, we will do more questions so that it becomes much, much easier for you altogether. Right. So again, I know you are nearing conclusion. By the 30th of September, everyone would have been done. So for those that have not as yet written, know that for this preparatory examination, then your physical properties section on organic chemistry will be plus minus 29 marks. And I will give you more tips tomorrow as we do more questions. So, dying. Thank you so much for tuning in. I definitely enjoyed this particular session and I hope that you did too. Thank you very much. I'll see you tomorrow and enjoy the rest of the evening. Good night.